Now going back to the previous video, three modes of tool failure. We have the fracture failure, which is to do with excessive loading, or which has to do with like excessive cutting speed. We have temperature failure, when the temperature of the tool become very high and it loses properties and it fails. Then we have a regular wear and tear, gradual wear, which depends on the different factors. These are an equation for the tool life, which we will have a look in a minute. Now, we prefer the tool to wear gradually over a period of time. Now, whenever you buy a tool for machining, it has a life that many hours. So it attached that many hours, work hours, and that's how it should fail. So over a period of time, they actually say like you can replace them or you can move it. Its properties will degrade and you won't be able to use that one on certain materials over a period of time. Fracture and temperature failures are permanent failures. Gradual wear is preferred because it can give you maximum life of the tool. Now, gradual wear occurs at two locations on the tool. Crater wears occur on the top rake face and the flank wear on the side of the tool. So there are two types of gradual wear and tear. Now, the crater wear, that's where you will actually see the crater wear, and the flank wear is the one you can actually see on the side. Top is crater, the side is the flank wear, so you can actually see that one. So these two, the top one and the side ones, are the principal locations of the wear and tear failure. So that's what is preferred. The reason is the normal wear and tear of the material. For example, let's say you got any tool over a period of time, because you're using it over and over, it's cutting the other material, so it is going to fail over a period of time. Okay, now this is a graph between the cutting speed on the y-axis and the tool life. That's a tool life in minutes. The cutting speed is feet per minute, how many foot it's cutting per minute, and that is in minutes. If you have a low cutting speed, if you have a low cutting speed, the tool life is very high. If you look at the bottom end, tool life is like 100 minutes, let's say, and the cutting speed, if you have a look, is very low. It's like 100 feet per minute. As you increase the value, of the cutting speed, let's say is at the highest value here is like around 300, the tool life is like around 1 minute. Now, this is not in minutes, this is a log. This is the log scale, which means the log scale is you need to multiply that by 10. So log 1, log 2, log 3, log 5, log 10, log 20. This is a log scale. Log scale is actually a multiple of 10. If you get an earthquake 7.8, the earthquake 7.9 is 10 times stronger than 7.8. It's not 0.1, it's 10 times stronger. Okay. Now, the Taylor tool life equation, around 1900, the equation is V T to the power N. The N is on the top of just the T, equals to the C. V is the speed, cutting speed. T is the life of the tool. N and C are the parameters. They depend on the feet, depth of the cut, work material, tooling material. So if you want to find the N is the slope, the gradient, change in Y over change in X of the material. And C is the intercept on the speed axis. So if we go back, this value here, 300, is the intercept on the y-axis. And if I want to find the gradient, that will give me the N value for the tool. Okay. Again, same thing. These are the typical hardness values, relationships for different type of tool material. Ceramics is on the very top, but ceramic tools are very expensive as well. And then the plain carbon steel tools are at the very bottom. So if you increase the temperature, the tool loses hardness and everything, and then it will not be effective cutting tool. Now then there are certain values for the C and N. Now C is in minutes per meters per minute, and it's also in feet per minute, depending on how you use it. Now for a high speed steel, the value of the N is 0.125, and the value for the C is 120 meters per minute. Cemented carbide, the value of the N is 0.25, and the value of the C is 900. For the ceramic steelwork, the value of the N is 0.6 and the C is 3000. So if we go back, we have a look at this equation. If the value of the C increase, the tool life increase. If the value of the N decreases, if you have a smaller number here, then you will have a higher tool life. Yeah? The bigger the number, the smaller the tool life is. Okay. Now then we have a cutting fluid. Now we use a cutting fluid. Now the purpose of the cutting fluid is to make sure the tool does not become hot. The temperature of the tool, cutting tool, is low. Otherwise, the cutting tool will lose its efficiency. The wear and tear will increase. The other function of the cutting tool is to also remove the material that's already been cut. So it reduces the tool chip and tool work friction as well.